Well, hi guys. This video is going to be over polar coordinates, converting to rectangular coordinates, and doing some slope on polar graphs. And the our coordinate system that we graph on, the XY thing that you mostly use, is only used to find a point in space. And we can use another way, polar coordinates in this instance, in order to locate that point in space. You are used to an XY coordinate system, but we can also identify a point in space by the distance from an origin, wherever we fix that origin, and the counterclockwise rotation, the theta that we have to use to get to that radius. So we're going to talk first of all about going back and forth between these coordinates. So going back and forth between r comma theta and x comma y. But they'll both will just identify a point in space. Here's some polar coordinates. This is the polar coordinate 2 comma pi over 6. Rotate pi over 6 counterclockwise, and this has a length of 2. Now you can, anytime we can have a negative radius with polar coordinates, and a negative radius would mean go to pi over 6 and instead of going out 2, go back through the origin 2. So you can have, it's okay to have a negative radius whenever we're dealing with polar coordinates anyway. So let's go ahead and practice one. How we convert back and forth is we take our trig ratios. Cosine theta is equal to x over r. This is the same thing as like the adjacent divided by hypotenuse, but I want you to think that as x over r. So if you cross multiply both sides by r, that's how you get this formula right here for x. That's like your x coordinate. And the same thing is true for sine. Our sine of theta is y over r, which is the same thing as opposite side over hypotenuse. Cross multiply both sides by r and you get y equals r sine theta. So let's go ahead and practice one. Let's say I have the polar coordinate 4 comma pi over 6. And let's convert that to what's called rectangular coordinates. So x is going to equal r cosine theta, where the r is 4 and theta is pi over 6. And our y is going to equal r times the sine of theta. So for our x coordinate, we're going to do 4 times the cosine of the angle pi over 6. And of course, pi over 6 is right here. Think of this as a 30-degree angle, 60-degree angle, 90-degree angle. Pi over 6, you label your triangle. Put a 1 across from the 30, a square root of 3 across from the 60, and a 2 on the hypotenuse. And you see the cosine is the adjacent over hypotenuse, or the x over the r, and this is times the square root of 3 over 2, which would be 2 square roots of 3. And then the y coordinate would be 4 times the sine of pi over 6. The sine of pi over 6 is 1/2. So that's going to give me 2. So converting this to Cartesian, or sometimes called rectangular coordinates, we would get 2 square roots of 3 comma 2. Okay, so let's talk about a couple of formulas you need. How are you going to get r from x and y? Like if you had to go backwards from your Pythagorean theorem, you can get r by taking the square root of x squared plus y squared. And how do you find theta? Well, your theta is arctan of y over x, because if you're trying to find this little angle theta here, and you had some y coordinate and some x coordinate, the way you find this angle is you set up the ratio tangent of theta equals y over x, and then you arctan both sides. So that's why we have that equation. That's basic stuff you should have done in pre-cal anyway. Now let's get down to actually finding slope and things like that. Just like with parametrically, dy dx, if you're dealing with r's and thetas, can be found by doing dy d theta divided by dx d theta. And provided, of course, that dx d theta is not 0, because if dx d theta is 0, then your slope is undefined. Or, I'm sorry, if dx d theta is 0, your slope would be undefined. And then something weird happens if we get 0 in both places, but I think we're going to see an example of that in just a second. So let's take a look at an example. How about r equals 2 minus 2 cosine theta? And what we want to do is we want to find out, where does this polar curve have horizontal tangents? Now, horizontal tangents are going to come from your derivative equals 0. And if your derivative is a fraction, then that's going to mean that the top is equal to 0. So we want to find out when dy d theta is equal to 0. And of course, if you wanted to find out vertical tangents, you're going to have vertical tangents anytime the denominator is 0 or dx d theta is equal to 0. So let's take a look at this. Let's find dy d theta and dx d theta by actually finding equations for x and y. So x equals, remember from your conversions, r cosine theta, and y equals r sine theta. So here is r, right there. So for this curve, x equals r, which is 2 minus 2 cosine theta, times the cosine of theta. And y equals r times the sine of theta. So this gives me a way of finding x and y in terms of theta so that I can find dx d theta and dy d theta. So let's answer the question, how about maybe the horizontal tangents? The horizontal tangents are going to come from dy d theta equals 0. And again, I'm going to give this little caveat. We cannot let dx d theta also equal 0. So let's find dy d theta. Here's our y equals equation. It looks like I'm going to have to use the product rule. So dy d theta is going to be, remember our product rule is the first times the derivative of the second, of course the derivative of sine is cosine, plus the second times the derivative of the first. Now the derivative of 2 minus 2 cosine theta, of course the derivative of 2 is 0. The derivative of the negative 2 cosine theta, we can just let the negative 2 stay there and take the derivative of cosine. Derivative of cosine is negative sine, so that makes that negative 2 cosine theta equal to 2 sine theta. The first times the derivative of the second plus the second times the derivative of the first. So let's clean this up a little bit and see what we have. 2 cosine theta minus 2 cosine squared theta plus 2 sine squared theta. And if we want to set this equal to 0, then I need to have one trig statement here. So I'm going to take advantage of our Pythagorean identity that says cosine squared theta plus sine squared theta is equal to 1. And I'm going to substitute for this sine squared. So if you solve that for sine squared theta, you get sine squared theta equals 1 minus cosine squared. This is going to allow me to solve this equation. So I've got 0 equals 2 cosine theta minus 2 cosine squared theta plus 2 times 1 minus cosine squared theta. See that substitution I made there? And I'm going to have a quadratic in terms of cosine squared. This is going to be negative 4 cosine squared theta, because I distributed that 2, plus 2 cosine theta plus 2. So now I have a quadratic in terms of one trig function. Let's go ahead and divide this through by negative 2. There we go. I wanted to have my squared term positive. All right, let's see if we can't factor that. Let's see, this will be 2 cosine theta and cosine theta. And then let's see, how about minus 1 and plus 1? Let's see if that works. 2 cosine squared minus 2 cosine theta. Yeah, there we go. So we set both of those equal to 0, and so we have the two equations. 2 cosine theta plus 1 equals 0, and cosine theta equals 1. So cosine theta equals negative 1/2, and where does cosine theta equal 1? Well, the answer for cosine theta is negative 1/2. That's at 2 pi over 3, and also at 4 pi over 3. And then where cosine is equal to 1, well, that's just at 0. So this looks like my 3 places where I'm going to get horizontal tangents, but I got to be careful. I wonder if any of these 3 angles for theta would make dx d theta also equal to 0. Let's go take a look at a picture of this. We've done a bunch of factoring and stuff, and I mean, these are pretty pictures anyway. So it's a way that you can maybe give that significant person a picture of a flower, on a calculator, and you can all be geeky about it, but still be, all nerdy in a real cool kind of way. And math is love anyway. So let's go take a look at this. Here's a picture of y equals 2 minus 2 cosine theta. And it's this cool little Pac-Man, little heart-looking thing. And let's go calculate. So I'm hitting second trace. And I hope that it registered. Maybe I might have to hit trace one more time there. There it is. I had to hit trace. Anyway, and in calculate, we can find a value, dy dx or dr d theta. So let's go down here to dy dx. And we said at 2 pi over 3 it was 0. Now the calculator sometimes, especially the 84, gives you this weird long big ugly decimal, e to the negative 6. That's basically saying like 0.00000006 or whatever. That's effectively 0 on the calculator, which I think it does that here. But you can see up here at 2 pi over 3, that's where we have that horizontal tangent. As the graph had gone through a rotation of 2 pi over 3, that's where we get a horizontal tangent. And let's go check the other one. Dy dx at 4 pi over 3. And that's probably going to be down there at the bottom, and it sure is. And of course, we got that weird 0, but that's 0. Now, theta equals 0 is at the very beginning of this graph. And let's go and take a look at that. Calculate dy dx when theta equals 0. Now, when theta equals 0, that sure does not look like a horizontal tangent line to me. I mean, maybe it's coming in this way as horizontal, but what about from this side, So if I type in 0, I'm going to get, oh, looky there, divide by 0. I guess that means then that dx d theta must also be 0 there. And so we don't get a horizontal tangent line, we get, come on, graph it again there for me. I guess I got to quit it first. Back to the graph. We get, that teetering tangent line thingy? So if they're both 0, you're not going to say that that's a horizontal tangent line. See, as we trace this through here, as theta increases, we're making this little pretty picture. And, well, my delay here is not going to do what I wanted to do. But if we go back there, that's close enough. At pi 3.14, I bet that's going to be a vertical tangent line right there. So anyway, tomorrow in class, you're going to practice some conversions. You're going to practice some dy dx's. And I also want to say something about this notation right here, the dr d theta. Dr d theta is not the slope of the tangent line. Dr d theta is how the radius is changing at a specific angle for theta. So, for example, as I graph this and I trace it, as I go through here, let me get back to where I was. Trace. There we go. So I go through here, I'm going to get back to the beginning. What is happening to the radius let's say right here? Is dr d theta positive or negative right now? Well, right now, the radial line that extends from what we call the pole or the origin, this radial line is getting larger. That means your radius is increasing. So if your radius is increasing, what do you think dr d theta is? And then out here, as I get out here all the way to the edge, what's happening out here to dr d theta? This radial line is getting smaller. So what would the value of dr d theta be somewhere around here at theta equals 3.66 radians? These radial lines are getting smaller. So it has nothing to do with the slope of the tangent line. It's what's happening to the radius. So anyway, you'll practice this, and you'll also practice with your graphing calculator, looking at some really pretty pictures. So I'm going to leave you with one real quick before we go. My favorite graph in polar mode looks like this. Let me adjust my window. Let's go -2. Now I'll do -1.5 to 1.5. And then -1 to 1. This is my favorite polar graph. It's like a little dragonfly. Isn't that neat? Anyway, I'll see you guys tomorrow.